The question I have is, what is the role of effective stress on the shear strength of sand? The effective stress has an influence on all types of soil, coarse-grained and fine-grained soils. But let's focus on coarse-grained soil in this video. But of course, the answer will be applicable to all kinds of coarse-grained soil, including sands, gravels, and so on. It turns out that effective stress is the only component of the stress that controls shear strength in a soil like sand. To understand this, let's go back to the elementary physics where we used a model like this, a sliding block model, in order to understand Coulomb friction, right? We learned that when a block having a weight W is pulled sideways, the interface between the block and the table is going to resist. And the maximum value of that is mu multiplied by W, where mu is the coefficient of friction. Sometimes we express that in this fashion where phi is the friction angle. Now let's say we apply these ideas to a system consisting of two sand particles. Supposing, say, there's a normal force of Fn at this contact. Now we shear these two particles like this, and when you do, the contact is going to develop a shear force to resist that, and there is a maximum value for that, and that maximum value is mu multiplied by Fn, where mu is the coefficient of friction between the two sand particles. So this is exactly what happens at a micro level when you shear a sample of soil. So it turns out that this Fn right here is exclusively due to the intergranular forces. In other words, Fn comes directly from the effective stresses. You may have water pressure between the particle, but the water pressure is not going to make any difference at all. In other words, it's not going to make a contribution to the shear strength of these two particles. So this is the primary role of the effective stress in soil mechanics. Effective stress controls the shear strength of granular materials like this. So to summarize, in granular materials, the shear strength is directly proportional to the effective stress. So if you don't have any effective stress, there's no shear strength. There's no difference between sand and a liquid in that case. All right? So when the effective stress increases, shear strength will increase. When the effective stress decreases, shear strength will decrease. Now let's consider a field deposit with a capillary zone and take 3 points, point A, point B, point C on a vertical line. The total vertical stress should always increase as you go down. So let me assume that I have 10 psi at point A and 20 psi at point B, 30 psi at point C. The pore water pressure should be negative at point A because I have a capillary zone, and therefore at the top of the capillary zone it should be maximum negative, right? So let me assume I have minus 20 there and 0 at point B, and then at point C I have plus 20, right? Now I calculate the effective stresses at these points using the Tesagi's effective stress equation. All I have to do is to subtract the pore water pressure from the total vertical stress. Then of course when you have a negative value for the pore pressure, then the effective stress becomes larger than the total stress, right? So these are the effective stresses at these 3 points, and you can see I have a higher effective stress at point A than point B and even point C. Usually you would think that the stresses will increase as you go down into a soil deposit, right? But this is not so when it comes to the effective stress here, and this is primarily due to the fact that in the capillary zone we have a negative pore water pressure. What this means is that the shear strength at point A is higher than the shear strength at point B, and the shear strength at point B is higher than the shear strength at point C. Here's a field situation where you yourself have experienced this many times in the past, but you didn't know why. This is something that happens at the beach. When the waves are not hitting the beach will be pretty strong. This is due to the fact there's a capillary zone above the seawater level, and therefore you have a negative pore water pressure in these regions, which increases the effective stress, which in turn increases the shear strength, and the sand behaves pretty strongly. As soon as a wave hits the beach, the sand becomes fully saturated, pore pressure increases, shear strength goes down, and the sand becomes weak. If you recall, you felt loosening of the sand under your feet.